Good day and welcome to this training session on earthing and grounding. Often spoken about, often a very confused subject, and hopefully after the short little course you will have a clearer understanding of what the difference is. So the two terms are often confused since both mean providing a zero reference potential to a wire or equipment. However, the reference zero potential differs. In the case of earthing, zero potential is the earth, while for ground it may be different. So what's the difference? Grounding. Grounding provides a common return path to a source of power and acts as a common point to bring all connected parts to a common potential. And this is pretty much the main difference. Most electronic circuits use a ground point. We'll see in upcoming circuit diagrams also how the ground connections at several points on the circuit are highlighted versus the earthing points. So earthing. The purpose of earthing is for protection and safety. The process of earthing involves putting a conducting rod or a conductor plate or earth mat deep into the ground to provide a return path for any fault current should a fault develop. So while grounding is designed to carry current, earthing is supposed to carry current only in fault conditions, and that is to keep personnel and equipment safe. An earthing connection is also often used to disconnect a supply in the event of a fault. So that's a key thing. Grounding pretty much carries fault or circulating current sort of all the time, whereas earthing is only supposed to carry current in the event of fault conditions. If we look at a typical supply transformer in the road giving you your power, we'll see that the neutral wire of the supply transformer in the road is grounded to earth in the ground. It provides a reference point in order to bring the neutral to earth to a zero potential and a return path for any fault current in the system. Now, while the transformer neutral is grounded, okay, it's in the ground, the metal body of the transformer now is earthed. Here we can see the difference. We're talking about grounded and earthed. So the metal body of the transformer is earthed. Both are connected deep underground, and they are connected separately. They're not connected together. So we see that the neutral is grounded in the ground with the earth spike, but the metal body of the transformer is earthed. Both in the earth, the soil, if you want to call it that one, they both serve different functions. But if we now look typically at circuit boards are designed to deal with leakage current to earth. Circuit boards can be damaged if there's no good earth connection to leak the ground current to. Leakage current is current that flows from either AC or DC in the circuit in equipment to the chassis or the ground, and can be either from the input or from the output. The leakage current in equipment flows when an unintentional electrical connection occurs between the ground and an energized electrical component or part of a conductor. The ground may be the reference point of zero voltage or the earth's ground. Ideally, leakage current from the power supply unit should flow through the ground connection and into the installation's earth ground. If the equipment is not properly grounded, the current will flow through other parts, such as the human body, or to other parts of the circuit. So what causes leakage current in a circuit board? Pretty much leakage current in circuit boards is largely due to imperfections in the insulators or materials that make the components, such as semiconductors and capacitors. And because of the imperfections in the insulation material, you're going to result in small leakage currents leaking or flowing through the dielectric, for example, in the case of a capacitor. Leakage current in power supplies may also occur due to electromagnetic compliance and EMI filters. These filters use wire capacitors between the live and neutral conductors. This causes some leakage current to flow from the neutral or the live conductor to the power supply casing, which is normally connected to the earth ground. Growing concerns about energy efficiency have led to now the development of electronics with higher power densities. Here we're primarily talking about IGBT modules, inverter modules. You're trying to miniaturize the system. You want it to work as efficiently as possible. So hence you're packing a lot more power. Your power density contained in a small area of components becomes much higher. So in grid-connected and industrial applications such as AC motor controls, UPSs, they need to keep manageable cable sizes. Keeping manageable cable sizes pushes power conversion to higher voltages. Whenever possible, using IGBTs in the place of thyristors permits power conversion at much higher switching frequencies. So IGBTs can switch much higher frequencies, and you can commutate your motors at much higher speeds. Basic characterization of high voltage semiconductor devices typically involves a study now of leakage current. Leakage current is the level of current that flows through two terminals of a device even when the device is switched off. When it's not operational, you get leakage current in the standby mode. Further to that, if moisture condenses on the surface, on the presence of a component, it will also form an electrical path between two electrodes. So typically, leakage current should always be lower than 3.5 milliamps as per the IEC 60950 regulations. This ensures that the current is very low and cannot harm a person who touches or comes into contact with a power supply or the metal chassis. You might have a half potential metal chassis that the PC board's attached to. A power supply with a good earth ground reduces leakage current significantly by providing a low resistance path to the ground. So here we can see a typical circuit. This is a single phase circuit, a live, neutral, and your earth wire. With time, you're going to get leakage current between these capacitors. The dielectrics might be faulty and they're going to circulate within this circuit and along the chassis. Here we could also have feedback. If this is a switch mode power supply, we could have feedback coming back from the bridge upstream of the switching transformer. All these are circulating leakage currents. Ideally, they shouldn't exist, but because of imperfections, they're going to circulate. So ideally, you need to trap these leakage currents and give them a much lower path through the earth to dissipate into the earth wire. Here's a typical example of a capacitor. They not necessarily have to be an electrolytic capacitor. These are electrolytics. Could be just normal non-polarized capacitors. But here's your insulation resistance. This could be your load. It could be any form of load which is supplying, that is doing the duty. But inside this component, you're going to have insulating resistance, which ultimately fails. And when it fails, you're going to get current leaking between these two electrodes because of the imperfections in the insulator. And this is going to circulate. Ideally, it's not meant to even exist, but it does happen in real-world situations, and that is why we need a ground to dissipate these circulating currents due to leakage of the insulator between the two electrodes. Leakage currents now, so these are purely capacitors, passive components. If we look now, leakage current in semiconductors like IGBTs is uncontrolled, which means it's parasitic. Current flowing across regions of semiconductors, structured devices, or device in which no current should be flowing. Then further to that, if we deal with quantum mechanics, which is a very real subject, so then at quantum level, we also have what we call quantum tunneling. And this is what happens the more we miniaturize electronics, the higher the risk of quantum tunneling prevails. And pretty much what is quantum tunneling? It's when electrons tunnel through an insulating region and they create leakage current. So here, if we look at a typical transistor, where you're going to get your gates, your source, and your drain, gate oxide tunneling, you're going to get quantum mechanics kicking in, and electrons are going to tunnel through the substrate and go to ground, and they're going to create leakage current. A better way to picture it is this. Typically, let's say we miniaturize a transistor, and this is where Moore's law kicks in, where there's a limit to how small we can make a barrier, and we limit it to how small we can make microprocessors and chips because of the effects of quantum tunneling. So here we see typically this could, if we look at classical mechanics, an electron will move along here and encounters a barrier. Depending on the pushing force or the electromotive force, the electron can ride over this barrier. And here you can see pictorially how this electron can just roll over. Now at quantum level, it doesn't even need to do that. It can reach a very minute level, a barrier, insulation barrier, and the laws of quantum mechanics say that particles also behave as waves. So it's a wave-particle duality effect, and this particle suddenly becomes a wave at quantum level, and waves tunnel through barriers. So therefore you're carrying a charge. It doesn't even need to roll over. It tunnels through as a wave function. And as it tunnels through, it's got charge and it develops leakage current. So this is typically what happens nearly all the time, is that barriers inside IGBT modules block electrons. Okay, so here's your barriers. What also happens in IGBT modules is that small amounts of electrons tunnel through the IGBT barriers, resulting in leakage current. And there's something interesting you can research about the wave and particle duality at quantum level. So here we're going to look at a typical electrical circuit, a block diagram, and what I've done is, here I've highlighted this is an earth, protection. So if we look further on this diagram, we will notice that we almost have a earth symbol, but it's an upside down smiley face. It's like a hemisphere. Here we've got one, here we've got one. So these typically all have to be joined up and form a ground. Interestingly, you'll see on the circuit board it says GRN for ground and not earth. So these aren't earthing connections, they are grounds. So why do we need to ground it? Grounding is to bring all the connected parts to a common potential and to create a pathway for any potential leakage current. And as we've learned, leakage current, even if you have the best material, you're not going to totally insulate because of quantum tunneling. If we look at a typical macroscopic design, here we have a typical VRV installation. Here we typically connect the grounds. Because of leakage currents in the circuit boards, everything has to be connected together to balance and bring all the leakage current to an equipotential. So all the VRV systems are to be grounded using the same grounding cable. And as I mentioned, the VRVs are now electrically bonded at the same low potential. This ground connection low potential now needs to be earthed. So we run, that's the lighter green cable. I go into my DB as a ground, not an earth, as a ground, and then I connect it. This we can create what we call a clean earth, and typically at the transformer you have a dirty earth. Far less circulating currents, so here your ground would come into your DB and it would now connect to an earth. You see there's two totally different symbols. So hopefully this has given you a bit of a better understanding of the difference between earthing and grounding. As I said, the words are used very interchangeably, but hopefully this has elucidated any confusion and given you a lot more clarity from macroscopic right down to the effects of quantum tunneling resulting in leakage currents across circuit boards. Thanks for joining, and subscribe to our channel, and you will get notifications of any of these short little pop-up videos in the near future. Thanks for joining, and I will be chatting to you soon.